Okay, so in this video, what we're going to do is we're going to discuss E and Z designation for alkenes. Okay, E and Z designation. So E and Z designation for alkenes, and this is section 5.11 in the textbook. This is section 5.11 in the textbook. So E and Z designation for alkenes. Okay, now for alkenes, what we've done so far is we've already talked about trans and cis alkenes. This, or it could be that, doesn't matter which one. We've talked about trans versus cis alkenes. Now this sort of a nomenclature, so trans versus cis, okay, so cis and trans, this is applicable to di-substituted alkenes, di-substituted alkenes. And what that means is, so di means two. So what that means is when you have carbons that are double bonded to each other, when you're looking at a double bond, you're basically counting the number of substituents on these double bonded carbons. So if I look at these carbons, we have one carbon here. This has one substituent. And we have another carbon here, which has another substituent on it. So they both have one substituent each. So overall, between the two carbons, there are two substituents. So it's a di-substituted carbon. And the same applies for these cis isomers also. So for di-substituted alkenes, we can talk about cis and trans. So since the two groups are pointing in opposite directions, this is a trans alkene. Since these are pointing in the same direction, it is the cis alkene. Okay, and also recollect that between a trans alkene and a cis alkene, they have similar connectivity, they have similar molecular formula. What's different about them is the three-dimensional arrangement. One is trans, the other one is cis. So that means these are also diastereomers of each other. So these are also diastereomers of each other because they are not mirror images of each other. They are stereoisomers that are not mirror images of each other. So they are diastereomers in a broader sense, cis versus trans alkenes. So the E and Z designation, okay, so E and Z applies to tri or tetra-substituted alkenes. Okay, so tri or tetra. That means when you have an alkene with 3 different groups around it or 4 different groups around it. Okay, and now that's key. It should have 3 different groups, or I think there are different variations to it, but if one of the double bonded carbon has 2 identical groups connected to it, then E and Z does not apply. Okay, so this is an exception. So if one of these carbons have 2 of the same groups attached to it, then the E and Z would not work. But it would apply to other tri, tetra. You can even apply to di-substituted alkanes, but for di-substituted alkenes, you can use cis and trans. You don't have to do E and Z. So let's look at a few examples because it's connected to the RNS. In some way, it's connected to the Kahn and Gold prelog nomenclature that we did for stereoisomer. So we'll look at a few examples to see how this works. Okay, so for assigning E and Z, and we choose, and let's choose a tri-substituted alkene to start out with. So let's say we have an alkene here, and that, and let's say this. So we have an alkene, and we have to assign E and Z configuration to this. So what we do is, for assigning the E and Z configuration, we basically consider the two double bonded carbons. That is what we're focusing on here. Okay, that is what we're focusing on. I don't want to use a star because it's not a chiral center. On this carbon here, and we're focusing on the other double bonded carbons, which are called, these carbons are called vinylic carbons. Okay, so carbons that are sp2 hybridized in a double bond, they're called vinylic carbons. So this one is also a vinylic carbon, VINYLIC, so vinylic carbon. Okay, so once we have the two vinylic carbons, we basically kind of split the double bond in two halves. And what we do is we focus on each vinylic carbon. Now I'm going to draw out the missing group here because realize that this is a methyl group and there's a hydrogen over there. And then based on the Kahn and Gold prelog kind of nomenclature, what we do is we assign priorities to these two groups that are connected to this. We have a hydrogen and a methyl group, so, or a carbon and a hydrogen. So this is priority 1 and this is priority 2. And we do the same for the other carbon atom. So when we look, there's carbon and carbon, so there's a tie, so we move beyond. That carbon is connected to one carbon, this carbon is connected to two carbons, so this wins. So this is priority 1, this is priority 2. Now, after you've assigned priorities, okay, after you've assigned priorities, if the higher priority group on each carbon is on the same side, okay, if the higher priority group on each, let's make it specific, vinylic carbon is on the same side, then it is Z. If they are on opposite sides, then it's an E. Okay, so it's an E or a Z. So coming back to this molecule now, what we see is for when we look at the two vinylic carbons, for this carbon, priority 1 is on the bottom. And for the other vinylic carbon, priority 1 is also on the bottom, and the priority 2s are also on the top. So that means this alkene here is a Z alkene. This is an example of a Z alkene. Okay, let's apply this to another example and then see how it works. So if we have an alkene where there is an OCH3. There's a methyl group. There's a fluorine. And there's a amino. I just came up with a hypothetical molecule. Okay, this does not have to be like a real molecule. But if you have to assign priorities, again, what we're going to do is we're going to focus on the two vinylic carbons. So we split the molecule such that we are able to focus on each of the vinylic carbons. So for this vinylic carbon, it's connected to a nitrogen versus a carbon. This is priority 1, this is priority 2. For the other vinylic carbon, it's connected to a fluorine versus an oxygen. This is 1, this is 2. And now what you notice is that for the two vinylic carbons, priority 1 are on opposite sides. In some sense, they are trans. Okay, priority 2 are on opposite sides. In some sense, they are trans. So when we have this situation, then we say that this is an E alkene. Okay, so this is E and Z. Now, quickly, I'll show you an example why it would not apply when you have two of the same groups. So if I have an alkene like this, let's say, okay, let's say that's my alkene. Now, when I consider this for this first vinylic center, okay, we have an ethyl group versus a hydrogen. So this is 1, this is 2. But on the other side now, they're both methyl groups, which means I'm unable to assign a priority over here because they are both identical. So I cannot differentiate the two. And so that is why when a carbon has two identical groups, when one of the vinylic carbons has two identical groups, then you cannot assign E or Z. In fact, you cannot even assign cis and trans in this particular case. Okay, so that's where E and Z has a limitation, or cis and trans has a limitation when a carbon has two identical groups. So that's, again, assigning sort of configurations to these diastereomers. In some sense, it's a configuration because the E and Z is telling us their three-dimensional arrangement. And configuration is basically the three-dimensional arrangement of groups in space. That is what configuration is. So the E and Z can be applied to alkenes. We will revisit this in chapter 8 when we talk about alkenes in more detail. You know, we're going to come back to this nomenclature and we're going to use E and Z. So yeah, so that is a discussion on E and Z. Again, it is basically builds on the RNS that we did for enantiomers and diastereomers. It's the same sort of rules that you apply. Okay, I hope that helps.